Start.
Okay. So I start the lecture. So mainly I'll talk about tensor categories arriving from subfactor today. So let M be a type 3 subfactor with finite index. And we also assume it has a finite depth. Then the finite depth condition means the following. So let gamma be the canonical endomorphism. Which I explained yesterday. So this is some endomorphism of M, large algebra. Then the finite depth condition means that we look at the power of gamma and look at the irreducible decomposition. Any positive integer. Then we get finite depth condition means that we have only finitely many irreducible endomorphisms up to unitary equivalence. Irreducible. So lambda r. Then so we have the following. So each has a finite index, finite dimension. Then for each I, we have some j such that a bar of lambda I is equal to some lambda j up to unitary equivalence. So this finite set is closed under taking the conjugation, and also sum of lambda I, one of lambda I must be the identity. So I level of lambda 0. So lambda one of them is the identity endomorphism or automorphism. And also, if we compose lambda I and lambda j, then this has an irreducible decomposition within this finite set. So the irreducible decomposition is of this form where nk is a multiplicity.
Depending on I and j?
Yeah, depending on, yeah. So if we fix I and j, then we have the coefficient nk, that's the multiplicity of lambda k.
So in general, n has 3 indices, I, j.
Yeah, that's right. It's like a fusion structure. So this basically then gives a fusion that so-called fusion category. Where Dave talked about two categories, but here I just talked about an ordinary category because we have only one algebra. So here we have only one algebra, which is actually M. So this is everything is an endomorphism of M. So the objects are of this endomorphisms of this form. Okay, finite sum. So they are objects of this tensor category, and the composition is the tensor product operation, and morphisms are this home space in the sense of intertwiners of endomorphism. And then they give some kind of tensor category, and usually it's called a fusion category. This means that so we have a system which is closed under taking the conjugation and also taking the product and the irreducibility composition. So one easy typical example of such a fusion category is the unitary representations of finite group. So we take a finite group and consider all irreducible finite dimensional, all finite dimensional unitary representations. Then we have a notion of irreducibility composition, and because the group is finite, we have only a finitely many irreducible representations, and we have a notion of tensor product, and then tensor product has an irreducibility composition like that, and we have the identity representation, and also we have a so-called contra gradient representation, which corresponds to this conjugate operation. So this, and also we have a notion of ordinary intertwiner between representations. So this is the fusion category.
Unitary is essential.
Well, it doesn't matter so much, but actually I didn't talk about the unitarity of this, but we are, in subfactor theory, we are essentially interested in something called a unitary fusion category. Then it corresponds to unitary representation. So this is one example. Then we also need a graphical calculus, which was already introduced by Dave. But unfortunately, I have a different convention, the opposite convention from the one used by Dave. So I compose map from top to the bottom, the other way. Yeah, maybe this is not an optimistic convention. So each wire is an object or endomorphism. And instead of a coupon, he used, I just write a dot, and this is a morphism. So is oriented. So this kind of picture. So this means T is an form from lambda to mu. So this is a typical thing. Or also, if we have triple points like this, we draw this picture. It means that T is a form from lambda to mu. And so we compose morphisms in this way. So so I compose from the bottom, from the top to the bottom. So T is, this is from lambda to mu. Yeah. So I use this kind of thing. Then we have cap and cap, which already also appeared in the talk of Dave. So we have this picture, lambda. Then this is mean that so this has an orientation, but for up to this point, it can give us the orientation, then we get the conjugate thing here. And here we have no wire anymore, but here we have an invisible wire which represents the identity object or identity endomorphism. So this picture, so I put T. This picture represents some, there is some canonical choice of T containing from this way, so lambda bar. Then also for the other direction. Then so as David explained, so we have this equality. So here we have identity here, and here we have some intertwiner, and here we have another intertwiner. So this picture is a composition of these two intertwiners. And this is really, so we have no dot, it means that we have the identity intertwiner, so just one. So this means that the composition of these two is equal to 1, and also the composition of these two is equal to 1. There is some normalization convention, but it's not essential, so I omit details. So this is one graphical method to draw intertwiner, but then the important thing is braiding. Okay. So our in the tensor category, so we have the tensor product operation, but it is actually a composition of endomorphisms. So if we have two endomorphisms of some algebra, infinite dimensional algebra, and if we compare the composition lambda mu and the composition mu lambda, there is no reason to expect any kind of relation between the two. These two can be entirely different. So usually they are different, entirely different. So this is a kind of non-commutativity of the tensor product, which is different from that example of representation of finite group. In the case of finite representations of finite group, so we have two representations, then pi tensor sigma and sigma tensor pi are naturally unitary equivalent, but we don't have such a commutativity here. So this is a general situation on the subfactor setting. So in the fusion category, we have no commutativity of the tensor product or composition operation at all. But sometimes, in some nice situations, we do have this kind of commutativity. Commutativity up to unitary equivalence. So we have lambda mu and mu lambda, and actually we use this kind of picture. So this picture represents an intertwiner homomorphism from lambda mu to mu lambda, and this picture is epsilon lambda mu. So this is actually unitary operator, unitary intertwiner. So I should. So lambda mu is equal to mu lambda up to this adjoint of unitary operator lambda mu. So this means that the epsilon lambda mu is an intertwiner from lambda mu to mu lambda. And actually, the reason I draw this over-crossing is that we have a notion distinction between over-crossing and under-crossing. So maybe I should write positive crossing. Then, so the other one is this picture, so lambda. This is epsilon minus. Well, it depends just a convention, a matter of convention, which is plus and which is minus. So this is another intertwiner from lambda mu to mu lambda, and so we need, for example, this kind of thing. So here we have one epsilon operator, and here we have another epsilon operator, and but graphically this picture should be equal to this. This is just an identity operator. So, so we need this kind of thing. We require this kind of thing. That's the meaning of braiding. So we have some relations which corresponds to a topological operation of this kind of wires. So, then it turns out that it's enough to require the following type of relation. So basically, we have some this one is and I omit labels such as lambda, mu, and so on. So here on the left-hand side, so from the top to the bottom, here we have a braiding operator here, that's a unitary operator. And here we have some intertwiner for this triple. So this is a composition of two intertwiners. Here we have one thing here, intertwiner, and we have one braiding here, another braiding here. So this is a composition of three operators. And we require that the composition on the left-hand side is equal to the composition to the right-hand side. And also for the other type of crossing, and also upside down. And basically, so this is the notion of braiding. So sometimes braiding exists, sometimes doesn't exist. But so we are interested in the case where braiding exists. And then, furthermore, we have a notion of non-degenerate braiding. This essentially means that the overcrossing and the undercrossing is really different. It means that if we can switch the overcrossing and the undercrossing for any mu in the fusion category, then this should imply this lambda identity. Yeah. So we say that the braiding is non-degenerate if this condition holds. And so if we have a non-degenerate braiding on the fusion category, it's called a modular tensor category. The name modular comes here because this is related to the unitary representation of the modular group SL2D. Okay, this word is related. So this is the notion of a modular tensor category. And the reason we are interested in modular tensor categories is the following. So there are lots of sources of modular tensor categories. So it's related to conformal field theory, which I explained in the last lecture next Monday. So some conformal field theories. And also quantum groups. They produce modular tensor categories. So in this sense, we have a rich source of modular tensor categories from other some mathematical objects. And also, if we have a modular tensor category, then we can produce certain topological invariant of three manifolds. Actually, it's called topological quantum field theory. Three-dimensional. So this name, topological quantum field theory of dimension 3, this is some kind of extended version of topological invariant, complex valued topological invariant of closed three manifolds.
Why three? What three?
Oh, that's not trivial at all. But this braiding basically produces a link invariant. Then a three-dimensional manifold arises from link through then surgery. So in this sense, three-dimensional manifold and links are closely related. And from a link invariant, we can produce invariant of three-dimensional manifold in this way. So that's why we have a dimension 3. Yeah. This is the detail I should introduce. So in this sense, a modular tensor category has a rich structure, and many people are interested in studying modular tensor categories from many different viewpoints. Then, so here, so today I'm talking about subfactors. So now I explain how to produce a modular tensor category from a subfactor. So the general subfactor of finite X produces only a fusion category, not a braiding. But then there is a method to produce a modular tensor category with braiding. And so for that, I have to explain two systems first.
Sorry, just to understand, the way we produced the fusion was looking at all the irreducibles inside of the
Yes.
powers. So
Yeah, right. Then we have no braiding in general at all in that situation. Then I have to introduce a new notion called Q system due to Rambo. And actually, this is some strange name, but somehow this name is attached to this notion. So, so this was originally formulated. In terms of endomorphisms, and I will give a definition in terms of endomorphisms. But actually, it's easier to understand this notion in the setting of bimodule. So I first start with bimodule. So in this situation, so we want to characterize a subfactor, and suppose this small algebra is given, and we want to find the larger one. Then what kind of data do we need? That's the question. Okay. So in order to get to a larger algebra, at least, so this is a vector space, so at least this is an NN bimodule. So we need some so larger n bimodule, so okay, and then bimodule X containing this one. At least we need such an n bimodule in order to get a larger factor n. But of course, this is not enough because this X is just n bimodule. And basically, in order to get a larger algebra, what we need is a multiplication structure of X. And actually, this multiplication map that they say, maybe N, this is a bimodule form. So basically, multiplication is characterized by an abstract bimodule intertwiner, bimodule homomorphism from this X tensor X to X with associativity. So this is basically gives the product structure of the large algebra X. Well, I will need some details related to the completion matter, but it's not essential. So basically, this gives larger algebra and the multiplication there. So it should give a characterization of a subfactor or maybe the superfactor n for a given n. Then, in terms of we translate this into the setting of endomorphisms, then what we have is the following. Okay, so we have some type 3 factor, n, the smaller one, and some theta is some endomorphism of n. Then we need something corresponding to the embedding of n into x, and this is given by W. It's on identity theta. And then we have the multiplication map. So this theta corresponds to x. So that this is an intertwiner from theta squared to theta, but somehow it's conventional to use the star operation with the opposite direction. So we have x from tensor from theta into theta squared. So this triple, theta wx, is called the Q system. Basically, if we have an associativity, then I'm cheating a little, but basically we have. And graphically, associativity is written in this way. Equal with theta. So now, so this is here. This triple point is this x. So this is from theta to theta squared, and here we have theta to theta squared. So this composition is intertwined from theta to the theta cubed, and also this is from theta to theta cubed. And here we have different attachments of the wire, and so this means really means associativity or maybe dual. So this is a notion of a Q system, and then if we have a Q system, we can find M and also converge. So if we have a subfactor, actually super larger factor m containing n, we can find the Q system actually the finite index. Then, so this is one way to characterize subfactor. So in order to construct a subfactor, it's enough to construct a Q system. Then, and the following is the so-called Longo-Lenen construction. Start with system of endomorphisms, finitely maybe. Irreducible endomorphisms. Okay, on fixed factor m, type 3 factor m with finite range. And we assume that this is closed. This contains the identity and closed under conjugation and closed under the composition. By saying closed under composition, I mean that if we could take two and compose them, then we can make an irreducible composition within this finite set. That's the meaning. So this is really the setting of fusion category. So this is the initial data. So suppose this is given, then we want to. So if we have a subfactor of finite depth, we automatically have this kind of finite set of irreducible endomorphisms. Then, starting with this data, we'd like to construct a new subfactor, a new Q system.
So now we're starting with n and we don't know n. We want to find n.
Yeah, right. Actually, we use different letter. So we now only have m, that's in algebra, and we forget about n, and we construct a different subfactor. We consider m tensor with m opposite. This opposite algebra origin appears in the talk of days. That is, we just reverse the order of multiplication. So basically the same algebra, but only switch the order of the multiplication. Then here we have and in the morphism. So each lambda I is an endomorphism of M. Then this also produces an endomorphism, the opposite endomorphism on the opposite algebra, which is basically the same map. But then we have a direct sum. This is a finite direct sum. So this is an endomorphism of this tensor product of M and M opposite. And maybe we have a new some endomorphism. Then it turns out that this produces a Q system, part of a Q system. We can find. Okay, we can find some canonical. W1x. So that they make a Q system. So it produces a new factor or new subfactor. So we get the smaller factor is now M10 prime opposite, and we have some larger factor which has nothing to do with the original subfactor n. So we have some different letter, the letter R. So this is a new subfactor, so finite index actually. Then the finite index. Then so let's gamma be the canonical endomorphism of this one. So this is an endomorphism of R into the subfactor. Then we look at the tensor power of gamma and look at the irreducible decomposition. Then it turns out that this is automatically a finite depth, so we get a fusion category. But then the non-trivial, very nice thing is that this fusion category arising from the irreducible decomposition of the power of gamma is actually a modular tensor category. So in this way, starting with ordinary any arbitrary subfactor of finite depth, we can produce a new tensor category, which is a modular tensor category. So this is some very nice construction. And actually, this construction is originally due to Okniano in the setting of type 2-1 subfactors, and he called it the asymptotic inclusion. But then Long and Reren found this formulation using the Q system. And actually, this construction has an interpretation which is purely in terms of tensor category. So, so this is a construction of subfactor, but we can interpret this as a construction of a new tensor category from a given fusion category. So a fusion category to a new modular tensor category. And actually, such a construction is known in the theory of tensor categories, and this is called the Drinfeld center construction. So this Long-Reren construction is a subfactor method to realize the Drinfeld center construction. And actually, this construction is fairly concrete, and we can explicitly compute this kind of thing in many examples, though it's not so easy. And actually, this is also called a kind of quantum double construction. Because a typical example is the one arising from a finite group. So it starts with finite group G. Then, so we start with the subfactor of this one, 6 points. Then we can apply the procedure I explained. Then we get the modular tensor category. From this, we get the fusion category first. Then this long-Borel construction with the modular tensor category. And actually, this modular tensor category is known under the name of the quantum double of G. The quantum double construction of a finite group. So this double means basically we double the algebra. So we make the M and M opposite. So this doubling procedure and tensor product procedure of the algebra is some kind of doubling procedure. Then we have some Q system and new algebra, which somehow magically perform the quantum quantizing procedure. So in this way, we get the modular tensor category. So this is a construction of modular tensor category, and this is a very interesting construction which has been studied by many people, also outside of subfactor theory. So this is one construction of a modular tensor category. So at least from any finite group, we can produce a modular tensor category. So this already gives a large family of modular tensor categories. But then we have a lot of examples of subfactors. I didn't explain much. But today we have a lot of examples of subfactors which are rather kind of exotic in the sense that they do not derive from any other known construction such as conformal field theory or quantum groups or whatever. So there are lots of examples of fusion categories arising from these some exceptional or exotic subfactors. Then by applying this general procedure of the kind of derivative center construction, we can produce a large family of modular tensor categories. So there are
by modular tensor category, you always mean non-general.
Yes. Yeah. So we always get modular tensor category. So there are abundance of modular tensor category beyond what is explicitly known today. Then, from a modular tensor category, we get the following, which I explained about name modular. So suppose we have a modular tensor category. Then we have irreducible object, or actually irreducible endomorphism in this setting. We use letters lambda, mu, and so on. Then we have this picture. And so this is actually this is a complex number. So this we have the invisible identity. So this picture is actually here we have one intertwiner, here we have one intertwiner, here we have a braiding, another braiding, and another intertwiner, another intertwiner. So this picture is a composition of 6 intertwiners from the identity to identity, which is a complex number. So this gives a complex number. And then basically, well, I'm ignoring some normalizing convention, but this number is written as S lambda mu. So this we have finitely many lambda. So this is gives a finite dimensional matrix S. Then T lambda mu is okay, chronic delta. So this is and this is self crossing. So again, so this is a intertwiner from identity to identity, which gives a number. So this T is a matrix, finite dimensional matrix, and here we have the chronic delta. So this is diagonal matrix. Then basically this gives unitary.
That's also the origin of the name modular. S and T are chosen by.
Yeah, I know. Yes. We now get the unitary representation of SF to D by sending. So SF to D is generated by these two matrices. And usually they are S and T matrices. So we send this to that F and this T. Actually, I'm skipping some normalizing convention, but essentially this is the correct thing.
So we can define S and T for a fusion category, though, right? I mean,
Um,
why not?
no, because we need a braiding here. Here we have a braiding.
But if it's degenerate, what happens?
Yeah, okay. So we can define these two numbers even if we have a degenerate braiding, but then we do not get a unitary
Okay.
representation.
So another way of saying what homogenious category is
Yeah,
so that
yeah,
S and T.
right. So actually, the non-degeneracy is equivalent to the fact that this is an invertible matrix.
Okay,
So, in particular, we get a unitary representation. So this is the meaning of the word modular. Then in the remaining time today, I talk about alpha-induction.
Is there relevance to Berlin?
Yeah, sure. That's right. So this S matrix is the one appearing in the Fermi formula. The relation between the fusion rule coefficient and S. And that the Fermi formula is true for general modular tensor.
Is there a claim that in general there's some ambiguity in the normalization, right? Because you get a representation of PSL2. Is it
Yeah,
the
right.
unitary setting?
Yeah, right. Actually, we need some normalization there. Then we really get we really get a unitary representation of SL to be.
And is that canonical in the unitary setting? Is there some canonical normalization that gets through SL2?
Yeah. Then, so the final topic of today's talk is alpha-induction. So we start with N with just a type 3 factor. And we fix a modular tensor category. Consisting of some endomorphisms of N. Then we want to find a subfactor of Q system. Q system. So that theta is an object of this. And suppose that we have such a two systems. Then it produces a subfactor, superfactor. If m containing m. Then this alpha-induction is a machinery producing an mn bimodule from an nn bimodule. From nn bimodules. Actually, in the modular tensor category. Here we have an endomorphism, but they really give nn bimodules. So here again, the alpha induction is formulated in terms of endomorphisms, but conceptually it's easier to deal with the bimodule case first. So I talk about the bimodule case next. So suppose we have some nn bimodule x and n, and we want to find an mn bimodule from this in some canonical way. Then there is some standard, rather trivial construction in this one. M. In this way, we can enlarge the x to the both sides. Then this is an m bimodule. But this construction is not interesting at all. The one thing is that even if we start with a trivial bimodule here, we do not get a trivial bimodule here. And if we have x tensor y here, then this procedure does not preserve the tensor product, the fusion rule. So we want to get some more canonical construction of m bimodule from n bimodule. So this is but not interesting. We need something more useful or canonical. Then we start with this one. Okay. We start with this one. Then from the left and from the right, we can tensor this m itself, but we make a tensor product only from one side. And we consider these two. So here we have a multiplication tensor product only from the left, and that one has only from the right. Then braiding means the commutativity, and in the bimodule setting, the commutativity of the bimodule tensor product, fusion product. So they are isomorphic by a braiding operator. Then okay. So here, so this isomorphism is isomorphism of n bimodule. But here we have the left action of m, and here we have a right action of m. And through this identification, so we have one Hilbert space which has a left action of m and the right action of m, and it turns out that they really commute. So in this way, we get mn dimension.
Which braiding did we use? Which we had two braidings, right?
Yeah, right. That's right. That's all. So this actually depends on a choice of braiding.
So we have two.
Yeah, we have two procedures. Two induction procedure. So this is conceptually easier, but somehow historically, which was studied in the context of endomorphism. So in the setting of endomorphisms, we have a lambda is an endomorphism of n, and we want to get some alpha lambda plus minus. This is a choice of braiding. And we want to get an endomorphism of the larger algebra. And this alpha is just a symbol. And so somehow we use the symbol alpha and we use the name alpha-induction because this is a kind of induction procedure somehow related to the classical induction theory of group representations. And here, this is actually an extension. So here we have an endomorphism of the small algebra. Then we want to construct an endomorphism of the large algebra. And then the way we do is that we actually extend the endomorphism of a small algebra to the large algebra as an endomorphism. This is what we do. Then actually, this is okay. So here we have the canonical gamma. Gamma, the inverse lambda theta. And actually here the gamma is the canonical inverse. Okay, I have here. And then theta is just a restriction of gamma to the small algebra. Then I turned out that here we do have the braiding because this theta is the abstract Q-system setting is actually this theta. So we have a braiding, so we have this situation. Then so the non-trivial thing is that we can apply gamma inverse here, but we can prove that the image of so here we have one endomorphism, another endomorphism, and the adjoint of unitary. Then it turns out that this part, the image of this part is contained in the image of gamma, so we can apply gamma inverse. And also from this definition, it's very easy to see that this is really an extension of the original endomorphism lambda. So in this way, we have we get a new endomorphism of the large algebra depending on the choice of the braiding. So this is actually a for endomorphism version of this construction. So
am I correct in thinking that both of these things have a non-trivial part? Over there, it's that you can do gamma inverse. Over here, it's that these actions
right.
commute.
That's right. Yeah. So this is due to Longo and Rayleigh originally, and that definition. And then on Shu studied this in more detail. And then in a completely different context of Liang studied this kind of thing in a completely different language, different picture. Then so we combine this in our work, in our events. And we have some unified machinery to study this alpha-induction. And then the graphical theory, graphical calculus I explained plays an important role here. But today I stop here. Thank you very much.
Any questions or?
So is it a functor? What are the properties?
Yeah, it's a functor, yeah.
A monoidal functor?
Yeah. Yeah.
Monoidal functor?
Yeah.
So what does it tell you about the relationship between the NN and MN bimodules? If you have so it's a functor from the NN bimodules to MN bimodules.
Yeah.
But they're not always equivalent. So it's what's the image or what's the image?
That's a different fusion category. It depends on the choice of positive or negative braiding. But if you look at the alpha plus induction, then so the original tensor category, the modular tensor category of NN bimodules, the image is another fusion category, which is not braided in general.
alpha plus, the image of alpha plus and alpha minus can be quite different.
Yeah.
But their intersection
Yeah, the
is a model
intersection is
tensor.
really a modular tensor category, and that had a good meaning in the setting of conformal.
You're saying it's a monoidal functor, so the image should look the same as the monoidal category?
So it's like you can draw pictures. So like you can do you have your Q system. So take your algebra in your
Yeah.
category,
Yeah.
then you can take the category of AA bimodules.
Right, right,
Since
yeah.
it's braided, modules is
Yeah.
these are bimodules. And so the point is that you have two free module functors from C to this, right? You can tensor on the A on the left or tensor on the
I understand, you're saying there's a monoidal functor from the original category to the category of AA bimodules? But
Yeah.
But isn't that an AA bimodule, this is generally supposed to be a different category of AA bimodules?
Yeah, it's a different category. So,
Oh,
yeah, so from the original category of AA bimodule, that's a factor to category of DB bimodule. Or some, yeah, or I write M. From NN bimodule to
Right,
NN bimodule.
I'm thinking of A as being your Q system here, so the okay, maybe I'm a little confused, I'll ask.
NN and MM are related by fusion category and AA bimodules.
Yeah.
Yeah,
So then there's the functor is going from here to the AA bimodules by just tensoring with A.
right, but in the general setting, there's no, they're monoidally quite different,
Yeah,
dual categories. You're saying here there's a monoidal functor from the original fusion category to the category of AA bimodules.
that's what this is. Yeah.
Yeah, right.
For any,
Yeah.
Q
For general subfactor, in M, the two categories are completely different.
right.
But here we have one category of NN bimodule, modular tensor category. So that gives a very strong restriction, so that we have a factor from one to the other.
If A is on the left, right, A and X, right, then you can braid it, and then you can act A on the right. So A tensor X is actually a bimodule.
There's no restriction on the Q system here, like, it doesn't have to be like commutative or anything.
No, this is general. Yeah, so we have actually a distinction of commutative and non-commutative Q systems.
This is in general.
This is valid for both cases.
Any more questions?
Okay, thank you.